Good morning, all of you. In this session, we'll discuss about entropy calculation in different processes. We have already explained the entropy calculation in reversible isomeric process and reversible isothermal process. So in this slide, we'll discuss first the entropy calculation for reversible isothermal process. Reversible isothermal process. Right? Well, we know that in reversible isothermal process, this temperature constant, and as per ideal gas equation, P is equal to mRT. Therefore, for fixed mass, gas constant and temperature, we can write that PV is equal to constant. So for this process, the guiding equation P1 Vn is equal to P2. Okay, and if we plot this process on this PV plot, okay, this PV is equal to constant. This is a curve like rectangular hyperbola. Okay, this is curve like rectangular hyperbola. This is process 1 and this is process 2. Okay. In one process, in both processes, the temperature remains constant. Let us suppose in this process, this temperature is T1. This T1 is constant. In this process, let us suppose this temperature is T2. At this process, this temperature is constant. Okay. Right. During expansion process, now we have to find in which process gas is expanded and in which process gas is compressed. This is very important and basic question. In problem, if somewhere it is given gas is expanded reversible isothermally, that means we have to plot the situation on PV and TS plot. This is initial step. So you need to understand very carefully how this curve will be drawn, how this process is represented on PV and TS plot. So in one process, let us suppose in either 1 or 2, the gas is expanded and in another process, gas is compressed. Okay. One thing important, you need to understand this basic concept. During expansion, volume increases. This is basic logic. And you know that in process 1, let us suppose this is state 1 and this is state 2. What we will observe here, in state 1, let us suppose this volume is V1 and this volume is here V2. In this condition, V2 greater than V1. So, in this condition, we can say that in process 1, this process is expansion process. Why expansion process? Because in expansion process, volume increases. In this condition, volume increases. Why? Because V2 is greater than V1. That's why the process 1 is expansion process at constant temperature. And the process 2 will compression process. This is at isothermal process. Okay. During compression, volume will decrease. In process 1, this is the reversible isothermal expansion. Because during expansion, simple volume will increase. And this process in volume will increase. Volume is increasing. That's why we can say that the process 1 is expansion process. Right? Okay. Now, let us define on TS plot. TS plot. Since this process is reversible isothermal process, so line will be horizontal because on y-axis the temperature is there, so line will be horizontal. Let us suppose this process 1 and this is process 2. In one process moving from left to right, and other process moving from right to left. Okay. Now we have to find in which process gas is expanded and in which process gas is compressed. In one process, gas is expanded. That means heat is added isothermally, reversible isothermal heat addition. And in another process, the reversible isothermal heat rejection. Now we have to determine in which process heat is added reversible isothermally and in which process heat is rejected reversible isothermally. We need to cross check this one. Right? Okay. We have simple fundamental basic. We know that ds is equal to dq by t. Whenever heat is added, in this condition what will happen? Entropy will increase. We have already seen whenever heat is added, entropy will increase. Okay. In process 1, let us suppose this entropy at point A, this is at S1, and at point at state B, the entropy is S2. In this condition, we can see that S2 is greater than S1. We can see. So we can say that the process 1 is this process 1. You can say that this process is reversible isothermal heat addition. In this process, we can say that heat is added reversible isothermally. How? Because whenever heat is added, the entropy will increase. Heat is added, entropy will increase. And in process 1, we are seeing that entropy is increasing. Why? Because the S2 is greater than S1. S2 is greater than S1. This S2. That's why the process 1 is reversible isothermal heat addition. So we can say that therefore the process 1 is reversible isothermal heat addition. Process 1. If suppose its temperature is TH, that in this process, the whole process, the temperature will remain constant. Okay, and this process with 2, this is vice versa. This is what is this one? This is reversible isothermal heat rejection. Why? Because we know that whenever heat reject, what will happen? Entropy will decrease. Entropy will decrease. That means in this process we can see that the final entropy is less than initial entropy. That's why in this process 2, so the process 2 is reversible isothermal heat rejection. Okay, so this is all about the basic fundamental. This is very basic concept. How to check, how to plot the reversible isothermal heat addition and reversible isothermal heat rejection on TS and PV plot. So whenever on PV plot, whenever gas is expanded, that means heat is added. because we know that whenever heat is added, gas expands. Whenever heat is added, work is done by the system. That means the gas will expand. During expansion process, volume will increase. Volume will increase. Therefore, the process 1 is expansion process, because in this condition volume is increasing, and in process 2 the volume is decreasing. That's why this is compression process. Similarly, on TS plot, whenever heat is added isothermally, entropy will increase, and simple in process 1 we can see that entropy is increasing when we move from left to right. That's why the process 1 is reversible isothermal heat addition, and process 2 is reversible isothermal heat rejection. Well, so this is the basic fundamental we need to understand carefully, so that we can visualize the situation, because proper visualization of problem is very important in thermodynamics. Though this concept is applied everywhere, it does not matter which paper you are studying. You need to visualize properly what is exact situation is, so that if problem is twisted in adverse condition, you can visualize the situation, we can understand the problem, and you can solve the numerical in easiest way. So this is very basic concept, you need to understand this one. This is the graphical representation of reversible isothermal process on PV and TS plot. Well, if it is clear, now we can move the entropy change in this process, in reversible isothermal process, right? This is quite simple. Let us suppose this is TS plot, this is the process, the lines should be horizontal, okay, right? This is state 1, state 1 to state 2, this is state A, this is state B, and process is 1, okay. In this process, just we are seeing that the heat is in this condition, heat is added. We have seen this one in previous discussion. Now we have to try. Let us suppose at this point entropy is S1, and at this point let us say entropy is S2. So we have to find del S. We have to find del S. That means entropy change in this process. Entropy change in this process. Right? Okay. Already we have two equations. This TdS is equal to du plus PdV, and TdS is equal to dH minus S. These are two important equations. We know, we are familiar with this equation, right? Just pick one equation. Let us TdS is equal to du plus PdV. We know that what is du? Cv dt. This is PdV. Since temperature is constant, therefore this dt will be 0. This implies TdS is equal to PdV, and this ds is equal to PdV by T, and we know that P by T is equal to R by V. Okay, PV is equal to RT, right? Okay, so this implies ds is equal to R dP by V. We have to integrate this one. And volume is V1, entropy is S1. volume is V2, entropy is S2. This implies del S is equal to S2 minus S1. This is equal to R ln V2 by V1. Okay. So this is the change in entropy for which process? This is reversible isothermal process. We can convert this equation in pressure form. Since we know P1 P1 is equal to P2 P2, this implies V2 by V1 is equal to P1 by P2. Therefore, del S at constant temperature, this equation can be written this R ln this P1 by P2. This equation can be written in this terms of pressure also. So what we observe here, finally what we have, the change in entropy del S at constant temperature, this is equal to either R ln V2 by V1 or either R ln P1 by P2. Both are same. Right? This is the entropy change for isothermal process, entropy calculation for isothermal, reversible isothermal process. Well, okay. Now we have to find next process is entropy calculation for reversible adiabatic process. Okay, in this process we know that there is no heat exchange. Okay, that means in this process there is no heat exchange. So in this process Q is equal to constant. If Q is equal to constant, that means dQ will be 0. And we know ds is equal to dQ by T. This implies since dQ is 0, this is 0. In this process S is constant. So this process is also called isentropic process. Isentropic process. So in this process there is no change in entropy. Why? Because in this process there is no heat exchange between system and surrounding. Whenever there is no heat exchange, that means entropy will remain constant. So on PV plot we have already seen in work. On PV plot we have already seen there are two processes. One is adiabatic expansion, another one is adiabatic compression. Okay, in compression we already the same concept. Whenever gas is expanded, volume will increase. Okay, we can see at TS plot. This line will be vertical. This process is isentropic. In one process it accelerates upward, and in the process the acceleration is downward. That is this process 1, this is process 2. Whenever gas is expanded, the temperature will drop. During expansion, what we'll observe here, temperature will drop. And during compression, the temperature will increase. So in process 1, since temperature is increasing, that's why you can say that this one is compression. And this process, this temperature is decreasing, that's why this is called expansion. So we need to represent this process both on PV and TS plot. Okay, and in this process there is no change in entropy, right? Next, our last process is polytropic process. Polytropic process. This is general process in which this guiding equation is in this condition Pb raised to n is equal to constant. In this condition, n is polytropic index. There is restriction over n less than 1 to gamma. Okay, where value of gamma is equal to 1.414. This is for air. So value of n, this polytropic index, always will be lying between 1 and gamma. In this condition, we know that this Ts is equal to d plus pdv. Let us suppose this is the situation. PV plot. This one is Ts plot. Okay. Let us suppose this is the PV raised to n is equal to constant. Well, so in this condition, what we'll observe here, this TDS is equal to du plus PdV. So this ds is equal to, and just one thing, okay. So TDS is equal to, what is du? CVDT. This is PdV. There, and so we have to put this value. This implies ds is equal to Cv dt by t, and this is p by t dv by p, or this Cv dt by t, and this p by t is equal to, not dv, okay, p by t dv, and this is equal to r dv by v, because pb is equal to rt. This is equal to ds. We have to integrate this one. When volume is v1, the temperature is T1 and entropy is S1. When volume is v2, temperature is T2 and entropy is S2. This implies del S is equal to Cv ln T2 by T1 plus R ln V2 by V1. This is one equation. This equation can be used for change in entropy for polytropic expansion process. Polytropic process, we can use next equation of dH minus VdP for open process. And what is dH? Cp dt minus VdP. So ds is equal to Cp dt by t minus V by t dP. This is Cp dt by t. What is V by t? R by p. This implies ds is equal to Cp dt by t minus R dV by v. We have to integrate this one. In volume is V1, temperature is T1 and entropy is S1. In volume is V2, temperature is T2, entropy is S2. In this condition, del S is equal to Cp ln T2 by T1 minus R ln V2 by V1. This is another important equation. So we can use any one equation as per given condition. This is open then right. So For polytropic process, by using this concept, you can find out the different, calculate the entropy calculation for this one. So for isothermal process, this is the equation, right? You can use any one equation, and for polytropic process, you can use either of this one or this one, depends upon condition. Okay, like closed and open system, they are simple. Okay, so this is all about the entropy calculation for all different processes. We have already discussed in 2 lectures how the different processes can be plotted on both PV and TS plot, and that means graphical representation of different process on PV and TS plot, and entropy calculation of different process. Okay, entropy calculation for different reversible process, right? In next lecture, I will discuss some numerical based on this one. Thank you.